Okay, so in that video we just watched, basically it was showing what can happen in a pipe network that maybe a designer wouldn't ordinarily consider. There's going to be unexpected things like air pockets traveling through the system when a large wave of water going through the pipe network traps a pocket of air, then that air comes out and drenches people and throws 1,000-pound manhole covers straight up in the air and lands on vehicles. So
was the manhole cover not welded or bolted down?
that one wasn't welded or bolted down. They probably thought, oh, there's no way such a big manhole cover could ever pop off. You know, nobody's going to lift that off and walk off with it. But it didn't happen to be humans that was a problem in that video. So let's take a look at these announcements. The lab number 8 that you need to submit on Tuesday, as it says on the handout for that assignment, what I'm looking for in the report is some example hand calculations that go along with calculating the head for a certain flow rate. And of course what we're doing in that lab is verifying Bernoulli's equation. And so you're going to be comparing the theoretical Bernoulli's equation, which we're talking about in class today, with the measurements that you take. And so comparing how is the pressure change actually observed versus how is the pressure change predicted by what Bernoulli's equation would say. So do some example hand calculations. For the rest of the runs, though, you can do it on the spreadsheet. Also with the spreadsheet, you're asked to come up with a couple of graphs, including the energy grade line and hydraulic grade line. And those graphs should be inserted into the body text. Don't just print out the entire spreadsheet, including calculations and graphs, but insert the graphs into the text. And the nice thing about doing that is sometimes when you're writing a lab report, you feel like, well, what are you going to talk about? What's the discussion? And it's very easy when you have graphs to just discuss the graphs, to talk about the trend that is observed, to talk about how it either does match what would be expected with the equations or how it doesn't, or try and explain why there is a deviation between observed and theoretical. And so if you're struggling for filling out the discussion, then oftentimes just putting the figure into the body text or the tables into the body text and talking about figures and tables can make it easier. And then you should also include the handwritten data sheet that you took in the day of the lab. Again, all of that and additional details on the handout itself. On Thursday the 24th, a week from today, you've got homework 4C, and this is the set of problems that have to do with Bernoulli's equation, which we're going to be discussing in class today. It is, yeah. Are there any more submissions of homework 4B? Question? Sort of. I mean, the lab report is those things that I've asked for. So if you consider that a full report, I'll be looking for the level of detail that's summarized on the rubric. But there are certain things in that rubric that you're not going to do. For example, you're not yourself going to develop procedures, and I didn't ask you necessarily to summarize the procedures or to provide a background. You don't have to include that sort of background information or a summary of how you completed the experiment in this case. But the discussion, for example, should have the elements that are identified on that rubric handout of what should be in the discussion. The graphs should be formatted in the way that are discussed on that summary rubric and so on.
The calculations kind of per run. I mean, we didn't get that last run, but is that going to affect any calculations that we do?
Yes, it will.
Okay. But we have a lot of time.
Well, I mean, it won't mess anything up. It's not going to give you bad calculations. It's just you're going to have one data point missing.
Right.
All right. Well, let's take an overview of where we've been in Chapter 4 so far. Remember, in Euler's equation, we were trying to address the question of how does pressure and elevation change as a function of local acceleration. So when velocity changes over time, and that's the definition of local acceleration, then pressure, and specifically piezometric pressure, changes as a result of that acceleration. And piezometric pressure could be the pressure itself, or it could be the elevation of the water surface above some datum. And so in the two different kinds of problems we worked, we'd have maybe an enclosed tank of water that was accelerating some direction, and we compared how the pressure was different between 2 points as it accelerated to the side. And in an enclosed tank, the water elevation couldn't change, but the pressure did change. If the tank is not enclosed, if the tank is open to the atmosphere and you start to accelerate it, then the water surface changes. And the pressure is still going to be different between 1 and 2, but the water surface is going to change as well. Euler's equation is what we use to characterize the effect of local acceleration. Bernoulli's equation is what we use to characterize the effect of convective acceleration. So when velocity changes as a function of position, then there's going to be a change in pressure or a change in elevation. Now, predominantly pressure, because in Bernoulli's equation we're usually applying that to an enclosed pipe network. And so it won't be these situations that where, you know, the tank is open to the atmosphere and it's accelerating, and so the water surface is itself changing. More commonly in Bernoulli's equation, we'll be considering changes in pressure. Now here's Bernoulli's equation, and I introduced it in lab on Tuesday. It has the same first two terms that the rotational flow equation had. And so the first two terms, this is called pressure head. You know, pressure divided by gamma is pressure head. It has units of length. Z is elevation head. It also has units of length. And you can tell P1 divided by gamma plus Z1, and then P2 divided by gamma plus Z2, that's the hydrostatic equation. So the hydrostatic equation was built into Euler's equation. It was built into the rotational flow equation, and now here it is built into Bernoulli's equation. It's the third term that is sort of where the magic happens. And this third term is the velocity head term. And remember, the difference between static and moving flow is that in static conditions the velocity is 0. But now here in Bernoulli's equation we can say that between location 1 and location 2 there's some difference in velocity. And we're not looking at a difference in velocity over time, we're looking at a difference in velocity over position. And so it's a convective acceleration that Bernoulli's equation is going to allow us to solve. Yeah.
Would we ever have a problem where we actually have to implement the pressure head? Because I know when we were talking about rotational flow, if one pressure head was canceled. Are we ever going to get to a problem where those are implemented?
So in the rotational flow problem where we were selecting maybe here like 1 and 2, it canceled out because we were touching the air, right? But yeah, in an enclosed system we had another example where we didn't cancel out those terms. You know, when we had a U-tube that was sealed and water was all the way up to the surface, remember we had this was 1 and this was 2, and we didn't cancel out the pressure head terms in those problems. And the same thing will be true when we're working with Bernoulli's equation. Sometimes we'll be smart about it and we'll find some location where the pressure is 0 and we'll make life easier for ourselves. But then other times actually we'll be using Bernoulli's equation to find some unknown pressure, so we don't always cancel out the pressure head term, because sometimes that's the objective of applying Bernoulli's equation, is to find an unknown pressure and how it changed.
If we have like one side open and one side not,
Yeah.
not all the way full of water,
Yeah.
would like freak like a vacuum?
It could, yeah. It depends on where it is. And so let's say we would have this one open, and so if it was full like this before and this one's sealed, then the water would want to go down, right? And it will go down a little bit, but it will be constrained by the pressure in here. And so that would be an interesting exam question where you're finding out, you know, there's a certain desired suction pressure in there and so on. Maybe, yeah. The only problem is I'd have to think of the problem. So I'm not feeling real creative today, so maybe I'll forget before I turn that into a good exam problem. All right. You have to know the limitations of Bernoulli's equation. Bernoulli's equation doesn't always apply, and in fact, for it to be a valid equation, you have to apply it for steady flow, meaning that conditions aren't changing over time, along a streamline, and it should be for an incompressible, inviscid fluid. So first of all, let's talk about what it means that we're applying Bernoulli's equation along a streamline. If here is a pipe transition, here the diameter has expanded. Streamlines, remember, are those lines that show us the direction that the flow is moving in. These are the streamlines, and we've got another one that's going like this. And then one of the streamlines in the center of the pipe is straight, and here's another streamline. All right, Bernoulli's equation should be applied along a streamline, and so it would be okay for me to say, I want to find out how the pressure changes between the center of the pipe here and the center of the pipe there, because I am along a streamline in that instance. But Bernoulli's equation would not apply if I was measuring at the top of the pipe here and then down at the bottom of the pipe there, because I'm on different streamlines now. So the first limitation, besides steady flow, is that Bernoulli's equation should be applied along a streamline. All right, and the other limitations are related to the fluid in question. The fluid should be incompressible and inviscid. Okay, fluids can include gases and liquids. So between gases and liquids, which one of them is more incompressible? Liquids. Yeah, gases can be compressed quite easily. And what we know is that so can liquids, but just not quite as easily. Of the two, between gases and liquids, liquids are a lot better at satisfying that constraint. According to Bernoulli's equation, it's really only valid if the fluid is completely incompressible. And neither liquids nor gases are the case. And even though gases aren't incompressible, we still apply Bernoulli's equation. We're still going to use it even when it doesn't apply, because the reality is Bernoulli's equation never applies. There's no such thing as an incompressible fluid, right? So we're going to apply it in spite of the fact that it doesn't apply. But what it does is that when you use it outside of the intended limitations, then you're just going to see a little bit of inaccuracy. It won't be as accurate as it would otherwise be. So on the case of incompressibility, Bernoulli's equation is better for liquids than it is for gases. What does inviscid mean? Does anybody know what the definition of inviscid means? It's related to viscosity. And what inviscid means is a fluid with no viscosity. And so that's another thing, that there's no such thing as a fluid with no viscosity, just like there's no such thing with a fluid that's incompressible. But certain fluids are better than others, right? A gas, like air, has pretty low viscosity. And so on the count of what qualifies as an inviscid fluid, air is pretty good. Water, not as good. Pancake syrup, very viscous. Bernoulli's equation won't apply as well in the case of an inviscid fluid. Later on in the semester, we'll get to an equation that can handle fluid viscosity. But Bernoulli's equation only applies perfectly for these ideal fluid conditions. Now, we'll still apply it even when we have a fluid that is compressible and is viscid, but when we are in the lab and our measurements don't match up exactly to what we'd expect, so you should write a note to yourself for the lab, you're not going to have exactly what you'd expect. You know, the reality of what you observe in the lab isn't going to be perfectly in line with what Bernoulli's equation would predict, partly because the fluid we were using has viscosity. Water has viscosity. Incompressible, water's pretty incompressible, so we're probably not breaking the rules too bad on that one. What about along a streamline? Are we along a streamline in the lab? Well, how are we measuring the pressure? In the lab, we have a pipe that's big, and then it narrows down through a neck, and then it expands again more slowly to the original diameter. All right. And does anybody remember how those pressure taps are set inside of the pipe? On the clear one, the arm-filled unit is a little bit easier to see since it's made out of a transparent plastic. It was just, there were little tubes going out like this. We'd have a spot here, we had a spot there, and as it was converging again, there was all these little tubes. These were piezometer tubes, and so maybe we're close to the same streamline, but not exactly. If there's turbulence inside of the pipe, then we may not be along the same streamline. And so Bernoulli's equation is more accurate for laminar conditions than it is for turbulent conditions because it's more challenging to measure conditions along a streamline in turbulent flow. That gives you a sense of some of the limitations, and we'll come back to that again. As we work examples and as we get deeper into the concepts, I'll remind you of the limitation, and in fact, in a future quiz, I may ask you to rehearse what are the limitations to Bernoulli's equation, and you'd say it is for steady flow along a streamline for an inviscid fluid that is incompressible. Those are the 4 limitations I'd want you to be able to sort of rehearse back almost as though they were memorized. All right, let's turn back to the concept of models that we've discussed before. An engineering model. You'll remember back in Engineering 104, for example, that we had the little solar power activity where the cart that I wheeled in here occasionally was meant to represent conditions at a hypothetical rest stop. We were using a physical model to represent what happens in reality. And that's the point of a model. It's a conceptual, mathematical, or physical representation of a system. And so a model might be an equation, like Bernoulli's equation. What Bernoulli's equation is doing is predicting how pressure changes. It's both a conceptual model and a mathematical model in the case of a Bernoulli's equation. A little matchbox car that you hold in your hand, that's both a physical and a conceptual model. It's showing you the concepts of a car, and it's represented physically. And so here is a wind tunnel experiment that's being conducted on a Boeing 747. Physical models can be used to measure how pressure changes in response to varying velocity. Bernoulli's equation is used a lot in modeling aerodynamics and aerospace applications. You may use an equation, a numerical model, to predict range. And these two equations are different, though. The top equation here is a fundamental equation. And this is a law that is based on observations in science that are known laws and relationships. These are not changing, whereas this is an empirical equation. And an empirical equation is just based on observation. It's an equation that the units may not work out, or that is just an estimate based on a lot of different experiences that have been documented. And so it's important to know the difference between a fundamental equation and an empirical equation. And so a small model can be used to represent a large full-scale model. And the boundary in an engineering model is defining what is the system that's being analyzed. In Chapter 5, we'll talk a lot about control volumes and control surfaces, and we'll keep track of what comes in and out of the boundary. The variables may change over time, and so the variables in Bernoulli's equation will be the velocity, the pressure, the elevation. Those are the variables, and then there are constants as well, the constant being gravitational acceleration, the unit weight of water. those parameters remain steady. Engineering models are important because it's often too expensive to build a full-scale prototype, and so instead of doing that, you're relying on maybe a computer program to predict how a pipe network is going to behave, or you're relying on a physical model in a wind turbine to shape a new wing to look for ways to increase fuel efficiency. Bernoulli's equation is very useful in modeling. It has a couple of different ways of being represented, and so this form of Bernoulli's equation is one way, but if we multiplied each term by gamma, it would look a little bit different. And in point of fact, Bernoulli's equation consists of two terms. There's the piezometric pressure term and the kinetic pressure term. And what it says is that along a streamline, the sum of the piezometric pressure and kinetic pressure is constant when you've got steady flow, incompressible fluid that has no viscosity. And so, in other words, you can write Bernoulli's equation like this, or you could write Bernoulli's equation like P1 plus gamma Z1 plus the density of the fluid V1 squared divided by 2 is equal to P2 plus gamma Z2 plus the density velocity squared divided by 2.
What's the benefit of that?
Oh, it's just what you've got the data in. There's really no benefit. If you're solving for pressure, then using this form of the equation saves you the trouble of having to move pressure out of the pressure head term. If you're solving for elevation, then maybe that form of the equation is better. They're essentially the same. You've just multiplied each term by the unit weight of water. Why is the velocity faster going out of this nozzle than was going in? Because the cross-sectional area of the exit is smaller. And the same flow rate going in has to equal the same flow rate going out. Inside of this nozzle, there's nowhere that water can accumulate. Like there's no storage reservoir inside of this nozzle. So if it's totally full with water and you put 1 liter in, then 1 liter will come out. But when we had 1 liter going in through a big area, then it was going in with a slow velocity. And to get that 1 liter out of a smaller cross-sectional area, then the velocity will be faster. And remember, this is the definition of convective acceleration. Convective acceleration is when the velocity changes as a function of position. It's the reshaping of the pipe diameter that's causing the velocity to change. And the reshaping of that pipe diameter is a function of its position in the flow field. Let's apply Bernoulli's equation here, where we've got a pipe and the diameter is increasing, and therefore the velocity is decreasing. So the inlet is 5.5 meters per second, and the outlet from this pipe transition is 0.6358 meters per second. So since the velocity went down, the pressure is going to have to change. Will the pressure increase or decrease at location 2? The pressure is going to go up or go down because the velocity went down. Think about, here's the equation, and it said that the velocity decreased from 1 to 2. And so if you look at, this, the sum of this, all 3 terms, are going to be equal to the sum of all 3 terms here. And it looks like the elevation is the same from both 1 and 2. So we can cancel out Z1 and Z2. And so if the velocity goes down, then P2 will be bigger than P1 was. So even before we start plugging numbers into the equation, we should expect that P2 will be larger than P1. Because that extra energy's got to go somewhere. It's going to go into the pressure. There was some energy in the fact that it was moving so fast. It was moving fast. It had kinetic energy. And now it's moving slow. That kinetic energy had to go somewhere, and it goes into the pressure. Okay, we've got a V1 of 5.5 meters per second, and the V2 is 0.6358 meters per second. P1 is 400,000 newtons per meter squared. The unit weight of water is 9810 newtons per meter cubed. And Z1 equals Z2. Bernoulli's equation can be simplified then. It's just going to be P1 divided by gamma plus V1 squared divided by 2G is equal to P2 divided by gamma plus V2 squared divided by 2G. All right. So I left out the Z term because the elevations are the same between the two. And so if I just want to substitute in the values, I've got 400,000 newtons per meter squared divided by 9810 newtons per meter cubed plus the velocity of 5.5 meters per second, square that, divided by 2 times 9.81 meters per second squared is equal to the unknown P2 divided by 9810 newtons per meter cubed plus the velocity 0.6358 meters per second squared divided by 2 times 9.81 meters per second squared. Okay, and the reason why I haven't isolated the pressure head term, the pressure term P2, is that I want to point out that this is 40.775 meters. This is 1.5418 meters. And that is 0.0206 meters. So at 1, this is 1, they're saying that 1 equals 2. The sum of the pressure head, elevation head, and velocity head at 1 is equal to the sum of the pressure head, elevation head, and velocity head at 2. Where's most of the energy at 1? Is most of the energy in the pressure, or is most of the energy in the velocity? It's the pressure. 40 meters of head is in the pressure, and 1.5 meters of head is in the velocity. And this is an important point, that unless the velocities are extraordinarily high, usually most of the energy is in the pressure head term. And that's especially true here. You can see at 2, the velocity head is almost negligible. In fact, sometimes we'll just ignore the velocity head because it won't account for very much of the energy. In this case, 0.02 meters of head is in the velocity head term when it's moving as slowly as 0.63 meters per second. And that's not a crawl. I mean, that's 2 feet per second. 2 feet per second is, you're not racing, but it's not stationary. So we can solve P2. P2 is 42.296 meters times 9810 meters, newtons per meter cubed. So that gives us that the pressure at 2 is 414,923 newtons per meter cubed. I'm sorry, newtons per meter squared. So it's about 415 kPa. Assuming what? assuming that this liquid has no viscosity, and assuming that's one of the four, same streamline, incompressible fluid, steady flow. All right. So steady flow, we can make that happen by just not changing the flow rate over time. So holding the valve constant, so not letting the velocity change over time. Steady flow, we can make it happen. We haven't violated that. Along a streamline, sure, you know, we're measuring at the center of the pipe for both, so we haven't violated that. Incompressible, water's fairly incompressible, but where we get into trouble is with the viscosity thing. The fluid does have viscosity, and it's not until Chapter 7 that we'll solve that weakness in our assumptions. So for now, we'll assume that the water has no viscosity, but really it does. So the pressure went up. The reality of what's going to really happen, like if we actually had one of these and we were actually taking measurements, the fact that water does have viscosity instead of the assumption that it doesn't, the pressure would be a little bit lower than this. That's what you'd see, is the pressure wouldn't be quite so high as 415 kPa. You know, if we had a pressure meter and it was measuring 400 here, then probably instead of 415, maybe it would be saying 410 or something. There would be a little bit of extra energy loss because of that viscosity. The viscosity, what does it do? It causes energy losses. So you wouldn't expect the pressure to be higher than this. It would be, this is a maximum. But the viscosity assumption that we're sort of violating a little bit causes energy losses that would be observed by a reduced pressure. We do in Chapter 7. It's going to be a group. We will. And the reason why we haven't yet is because, number one, we just barely started dealing with flowing fluids. You know, we're just talking about why fluids move, and we're looking at what would the pressure differences be under ideal conditions. And then once we understand how pressure changes under ideal conditions, then we'll move into how does pressure change under real conditions. And the real conditions is when there are energy losses due to pipe. Yeah. There are some pretty complicated empirical equations. Remember, we were talking about the difference between an empirical equation and a fundamental equation. We have fundamental equations that can predict how the pressure changes as a function of a velocity changing, but pipe friction, it's pretty ugly. I mean, we'll get into it pretty heavily next semester in hydraulic engineering, but we have to sort of bend over backwards sometimes to accurately predict what pipe friction is doing. All right. Any other questions on this example or just Bernoulli's equation in general? All right. This is an interesting picture. We've got a nozzle, and we're using a differential manometer. You remember manometers. The reason why we use manometers like this is that we can have a certain fluid, and the position of the fluid will help us to understand how the pressure is high in one place and low in another. Armfield? No, there wasn't a differential manometer in the experiment on Tuesday. There was a piezometer. Yeah. Yeah. So in this nozzle, the air is flowing through the nozzle, and we're using water as our differential manometer fluid. And air is more dense than water, and so it works great as a manometer fluid. And the other thing is that you can see the water, where you couldn't have two gases. You couldn't have like one gas as the manometer fluid and another gas going through there, because the two gases would mix. So just that as a preamble. But think about the air is going through this nozzle, and you can see that the cross-sectional area is decreasing. And what it says in this example statement is that the area at 1 is double the area at 2. So that means that the velocity at 2, how is the velocity at 2 going to compare to the velocity at 1, the air velocity? Since the cross-sectional area at 2 is twice that at 1, that means that the velocity at 2 will be double the velocity at 1. Let me write this on the board so it's clear. What we're going to have is that Q1 is equal to Q2. And that means A1 V1 is equal to A2 V2. Now, I sort of feel like I'm cheating you by telling you this now because this is at the heart of Chapter 5. We're jumping ahead a little bit in me telling you this. But you need to know it in order to solve this example. Since the area at 1 is twice the area at 2, so at area 1 is basically 2A2. For these two things to equal out, what we need to have is that V2 is going to be double V1. And so where we have V2, we'd say 2V1. And so now it equals out. We've got 2A2 V1 is equal to 2A2 V1. Symbolically, it can be a little bit confusing, but it makes sense that if you constrict the area that the air is flowing through, then the velocity will speed up. Now here in this example, we're measuring the pressure. Here it's going sideways to the flow, but then the end of this is actually intercepting one of the streamlines. See, this tube is actually, if we zoom in on what's happening with that tube, the air is flowing sideways and there's a stagnation point. Like one of these streamlines is stopping right at the mouth of the tube. And what it's doing is all of the velocity energy is being turned into a little bit of extra pressure at the opening of that tube. If you look at the water deflection here, the water is lower here than it is there. And so that means that the pressure is higher in here. So why do we have a high pressure inside of that tube? The reason why we have high pressure inside of the tube is that the wind is going along and then it's just dead ending into that stagnation there. And the way that you can think about that is if you had water flowing through a pipe and you put in a hole so that water's going to spray everywhere, but instead of that you put in a piezometer. Okay, the water level is going to rise this high. Well, let's say you put in another hole and you feed the tube down this way, and then it goes up. Will the water level be higher than or lower than or the same as it was when the tube was just going off to the side like that? Now we've got water flowing this way, and this opening is directed like it's getting full blast of the water that's going past. So who thinks that water level is going to be higher than it was before? Who thinks it's going to be the same? Who thinks it's going to be lower? All right, it's actually going to be higher. It's going to be higher because, you know, think about when it was, let's say that it's not yet directed into the flow. Well, if they're both going to be equal. And by the way, we're neglecting energy losses. And so forget about pipe friction for now. These are close enough together that pipe friction effects are negligible. So they're the same, but then as we move this down and open it up into the flow, all of a sudden it's getting this extra boost of energy because the energy that was in the velocity head is going to be transferred into the pressure head, and so that would cause the water level to rise a bit further. So Bernoulli's equation says if we compare what's happening between 1 and 2, where 2 is just before the opening of that second tube, then we can find out what is the velocity at 2, and we can find out the pressure at 2. But it's also possible to apply Bernoulli's equation at the tube opening. So let me write that here on the board. We've got a nozzle that's contracting, and this tube is a differential manometer, and we've got it coming like this. Okay, and the water is high here and low there. We've got some deflection, 10 centimeters. And the wind is slow here. The wind is fast, but then all of a sudden it stagnates right there. And that fast wind all of a sudden stops. So I'm going to call this location 1. I'm going to call this location 2. And then I'm going to take a look at what's happening just inside of the tube. So there's 1, 2, and then there's the tube location, where it's just inside that stagnation tube. I know that the velocity at 2 is twice that of the velocity at 1, and the density of air is 1.2 kilograms per cubic meter, and that means that the unit weight of air is 9.81 meters per second squared times 1.2 kilograms per cubic meter. That is 11.77 newtons per cubic meter. Bernoulli's equation says that the pressure head plus the elevation head plus the velocity head at 1 is equal to all of those things at 2. You know, that's the example we just solved, was comparing 1 and 2 in the last example. Well, we can go also between 1 and what's inside of the tube as well. So we can simplify this. By the way, since they're all at the same vertical elevation, I can cancel out the z terms, right? Since it's on the same plane, the same horizontal plane, I'll cancel out the z's. This tube is a stagnation tube. There is no air movement inside of the tube. The wind is going along and then it just sort of dead ends. It stops. The wind doesn't continue blowing through the tube. It would shoot all of the water out of there. And so conditions are static inside of the tube. That means that inside the tube there's no velocity. So what I'd like to do is I'd like to write Bernoulli's equation between location 1 and inside of the tube. So it's going to be the pressure head plus the elevation head plus the velocity head. And now the pressure inside the tube, the elevation of the tube, this location just inside the stagnation tube, plus the velocity inside the tube. Okay. The velocity inside the tube is 0 because it's a stagnation tube. Conditions are static in that tube. The elevation is the same between location 1 and this location right inside the opening of the tube. So that enables me to calculate the pressure in the tube as a function of the pressure at 1 and the velocity. The other thing I can get from, now this is Bernoulli's equation. I can take a look at the manometer equation and see what sort of information it's providing. The manometer equation says that I can apply the hydrostatic equation from 1 over to the tube opening, this location here, and I'll just apply the hydrostatic equation. So whatever the pressure is at 1, assuming static conditions, plus 0.1 meters times 9.9810 newtons per meter cubed is equal to the pressure inside the tube. Air pressure does change as you go up and down, but probably the pressure here at the opening is about the same as the pressure there. You know, we don't know how far apart they are, but what we're going to assume that everywhere inside of this tube the pressure is the same. That's a pretty good assumption. Air pressure doesn't change much as you go up and down because the density of air is so low. You have to go really long distances vertically before air pressure changes much. You've got to the top of a very tall building, for example, before your ears are going to pop. But you don't have to swim down very far before your ears start to notice it, because pressure changes more quickly in a liquid than it does in a gas, because gases aren't dense. So again, what I'm saying is the pressure is the same everywhere inside of the tube. So the manometer equation says we're going to go through this gas and the pressure is not changing. So the pressure here and the pressure at 1 are the same. We're assuming static between 1 and the interface of the liquid. Then we're going to go down through the manometer liquid, 0.1 times the unit weight of the water, and that's going to equal to the pressure of the tube. So there's a relationship between the pressure in the tube and the pressure at 1. In other words, we say that the pressure in the tube minus P1 is equal to 981 newtons per meter squared. That's the difference in the pressure. Now I can put that back into Bernoulli's equation. So if we continue with Bernoulli's equation, then we have the pressure at 1 plus the density velocity at 1 squared divided by 2 is equal to the pressure inside the tube. And I got that by multiplying each term by gamma. So P1 divided by gamma times gamma will just give us P1. Gamma times the velocity head term. Gamma divided by g is density. So density is gamma divided by g. And that's where, over here, we have density times velocity at 1 squared divided by 2 is equal to the pressure in the tube. Okay, and finally, what we're going to do is substitute in the information from the manometer expression. Here, the manometer equation told us the difference in pressure between the two locations was 981. This can be arranged as the pressure in the tube minus P1 is equal to the density velocity at 1 squared divided by 2. And we make the substitution, then we've got 981 newtons per meter squared. This was from the manometer part of the problem, is equal to, for the density of air, 1.2 kilograms per cubic meter. The velocity, 1 squared divided by 2. And then solve for V1. We get the V1 is 40.4 meters per second. Thus, V2 is double that. And we have the velocity at 2. So it's really interesting that we didn't necessarily have to know the actual pressure at 1 and 2. This differential manometer just measures the difference in pressure between 1 and 2. And knowing the difference in pressure between them is enough to find the actual velocity at 1 and the velocity at 2. Any questions from this example? Let's take a look at one more slide. Stagnation was at the heart of that last example. The idea that if you have a streamline going along, that means that the water has velocity. There's energy in that velocity. But then all of a sudden, that streamline stops. That means that there's going to be a loss of the energy that was in kinetic, and it's going to have to go somewhere. And it's going to go into a localized increase in pressure. That's what happens with a submarine, for example. As a submarine goes through the water, the front of the submarine, some of the water goes over the top of the submarine, some of it goes under. But there's a spot where the water is just stagnating on the front part of the submarine, and there's a localized increase in pressure along the leading edge of a submarine or along the leading edge of a wing. In the case of this, what it's showing is a stagnation tube it could be even just a straw. If you directed a straw down into a stream of moving water, what would happen is the water would either, if it was a really high velocity, the water would just blow all the way out of the straw. And you can prove that to yourself by taking a straw to a water park, and you know where the jets come out as you're about to go down the water slide. Just put the straw in there and the water would go squirting all over the place. But the velocity is a little bit lower. The water won't blow all the way out of the straw. It'll just rise to a certain level and then it'll stop. And how high above the liquid level it rises can be used as an indication of how fast the velocity is. It's like a velocity meter. How high the water level rises, it's going to go higher and higher with a big velocity, and then it will come down with a lower velocity. And Bernoulli's equation tells us how we can use a stagnation tube in order to measure velocity. Essentially, when you come down to it, you can say that the velocity before the water stagnates in the tube, the velocity upstream of stagnation, is just the square root of 2gl, where L is the distance above the water surface up to the height of the water that it rises. This is talking about like a moving river. So in this case, it's like an open to the atmosphere. And so you've got a river that's moving along, and if you put a tube down in a moving river, the water level will rise up above the surface of the water, that is the river itself, and how high it rises can be used to measure the velocity.
There's got to be as long as the water's at the same elevation as 2.
Yeah, so it's along a streamline to apply Bernoulli's equation, so 1 and 2 would need to be on the same elevation. Okay, so between now and Tuesday, you need to prepare the lab report, and you could get started on the homework assignment as well. That's going to be due on Thursday, but all we'll be doing in class next Tuesday is a couple more examples with Bernoulli's equation. You've got the fundamentals you'll need to solve these homework problems if you want to get an early start. So I'll see you on Tuesday.